Software Development Lecture Series co-hosted by the Computer History Museum. I'm Sanford Rockowitz, chair of the series. First of all, Laura Merling, Executive Director of SD Forum, is going to say a few words about the organization. Laura?
Hello, everyone. Thanks for coming. I think many of you have been to quite a few of the series. I see some familiar faces out there. At first, I want to thank Sandy for all of his work for the entire series. And the reason why I'm doing that is there's probably only a couple more left for this particular series, and we're looking for the next series. So if you have thoughts or ideas, I think Sandy would love the input, and I know we would as well. Do we continue this? Do you have other topics? Where else would you like us to go? Anyway, for those of you that don't know who Software Development Forum is, we focus on emerging technology trends and providing education to you and the rest of the community to try to say, hey, what's going on, whether it's wireless intelligence, whether it's grid computing, whatever the topics and technologies are. So again, if you have ideas, we like to hear them. But that said, the only other announcement I have is an announcement that I'm going to do for Bill Grosso very quickly. Next week on Tuesday, we have a home networking expo, kind of the connected home. So it's a series of 2 tracks. One's on content, one's on infrastructure within the home, and it's addressing different topics. Like I think TiVo's coming to show you their developer toolkit and talk about connecting your PC to TiVo and things like that. We have a broadband panel. Microsoft's coming to do a keynote on the future of the home 8 years from now and where it'll be. So there's some interesting things coming. That's next Tuesday, the 29th. All right, I'm done. Sandy, your turn. I'm done.
Thanks, Laura.
Thank you, everyone.
Well, we're delighted that the Computer History Museum is co-hosting this series. And as many of you know, the museum is videotaping the talks in the series for their archives. And John Toole, the executive director of the museum, is going to say a few words.
I want to really thank everyone, and it's been a real honor working with the Software Development Forum. We really have a lot of synergy. While this is about the future, we're about the history, recording the authentic history. We have a great program ourselves with a lecture which we join with you folks in having. Our next lecture will be in our new Phase 1, or Alpha Phase, building at 1401 North Shoreline Boulevard in our new auditorium on June 10th. It'll be Jurassic Software, the origins of consumer software. Stuart Alsop, Scott Cook, and a whole bunch of folks that are going to be at that particular lecture. But our role is really to preserve the history authentically and to really make that happen. We have hardware artifacts that go back 25 years. We've got software artifacts that go back 25 years. We're putting together, over the period of the next 3 or 5 years, a really first-class, world-class exhibition for people to really enjoy and to understand what it was all about and the innovators like we're going to hear about tonight. It's particularly happy tonight because Alan is one of our museum fellows, and it's a pleasure to be here, and it's a pleasure to work with the Software Development Forum. Thank you,
Thanks,
Sandy.
John. Well, as many of you know, the talks in this series are intended to answer, from a variety of perspectives, the larger issues of software development. And to this end, we've enlisted distinguished figures in software development who can share with us their thoughts and insights on how software can, should, and will be developed and the technologies by which this will happen. Simply put, the talks in this series are intended to answer the following question. What is it that leading-edge developers should be paying attention to, and why is it important? Now, as Laura said, we're coming to the close of this lecture series. We expect we'll have one more talk, either the final Thursday of May or the 1st of June. And we would very much like your feedback on what's worked for you in this series, what you've thought has been valuable, what might have been done better. And looking forward to the coming year, what might we look at in terms of a series addressed to a senior technical audience? What people would you like to see? What topics would you like to see addressed? And I know some of you might have caught the slideshow that was playing here earlier on as you were coming in. It included my email address, which is Rockowitz, Rockowitz, at Minsoft, MINSOFT.com. And I'd very much appreciate hearing from you, your thoughts on what we might do as a follow-up series next year. Our speaker tonight is truly a seminal. Pardon? With Alan Kay, it is a true challenge to keep it short. Xerox Fellow, Atari Chief Scientist, Apple Fellow, Disney Fellow, HP Fellow, President of Viewpoints Research Institute. The list goes on, and the awards goes on. Alan has said that the best way to predict the future is to invent it. And my God, has he walked the talk? His image of the Dynabook, sort of way back when computers filled rooms, sort of clued us into what computers might be, what a personal computer might be. One of the creators of Smalltalk, the first dynamic OO system. He developed key aspects of the windowing user interface that we all know. So it's a real honor to welcome Alan Kay here this evening.
Thank you. Yeah, thanks. You know, it's great to be back at Park, but of course this part of Park never existed when we were here. It was built after a whole bunch of us left. So this is actually a new part of Park. And since this is forum has kind of the fabulous paradox of being about the future of software but sponsored by the Computer History Museum, it opens a very wide range of possibilities for giving a talk. And so what I thought would be interesting is to start off with maybe a little bit of a kvetch about the last 20 years or so of non-development in so many areas. Take a look at there's some interesting 40th birthdays this year. There's a really interesting 35th birthday this year. There's a 30th birthday this year that are all, I think, have something to do with the future of software development. And many of these are what I would call really promising roads, not actually taken. Roads that had tremendous potential and actually paid off tremendously well many years ago. And then the vicissitudes of various things, including the way commercialization got done, these roads were not taken over the last 20 years or so, and I think to the detriment of most software. So the kvetch is a simple one. And actually this kvetch is pretty much the same about the last 20 years. And 40 plus years ago we made the same one because it was kind of IBM and looking at business and thinking of business as the ultimate target for trying to sell computers. And the problem with business and organizations of this ilk is that they are kind of an epitome of two conservative properties that most human beings have, not just in advanced societies, but in traditional societies as well. And one of these is called instrumental reasoning. Instrumental reasoning is a form of reasoning by which when a person is presented with an idea or a tool, they judge this idea or tool solely on the basis of whether it contributes to some goal they already have. Okay, and I think if you think about that, you can see that many, many people you know are basically instrumental reasoners. Only, as far as we can tell from working with children, only about 5% of children are not instrumental reasoners. So it's something that's basically built in. A person who's not an instrumental reasoner, when presented with a new idea or a tool, will actually transform themselves in the presence of the idea and the tool. And so these are people who are called early adopters that aren't just faddists. Some early adopters just want to be early, so they don't have much taste. But there are other people who respond actually to the new idea. And these people are to be found in each era. And often they are the ones who come up with things that are thought of as far-reaching visions that then unaccountably take many decades to actually spread out generally, even if they were a good idea in the first place. This happens over and over again. And the other allied idea is that we humans are very, very prone to do case-based reasoning. It's the main kind of reasoning built into our nervous system. So it's a compartmentalized way of dealing with past experience. Our legal system is very case-based. Engineering happened thousands of years before science because it was case-based. So you don't have to have a great theory if you're gathering up things that work. So you tend to make cookbooks of things, and you always basically start off that way. The problem is that you start losing. It's a great first-order theory and a bad second-order theory. So when the commercializations of PCs happened a little over 20 years ago, and it was aimed at business, it was basically aimed at a customer that didn't really even want the computer that much. And when they did want it, they wanted it for automating paper. So as McLuhan said, we were moving quicker and quicker into the future, but steering only by looking in the rearview mirror. And this commercialization almost completely occupied the space. So we'll come back to that a little bit. And of course, this has happened in history. So when the printing press got invented, and for the next 100 years or so, much of the printing that was done was to automate things that had been done by manuscript with monks, many of them religious tracts. And if you've seen a Gutenberg Bible, you will have maybe been astonished at how much it looked like a hand-drawn book. Gutenberg actually had more than 250 characters in his font because he wanted not just to do the upper and lower case, but every ligature, every abbreviation that the medieval scribes used, he wanted to duplicate those exactly. So he carved not just the 50 or 60 things that he needed, he carved 253. And then they brought in people, after they had saved all this money by printing, they brought in people to hand illuminate the books so they looked real. And the books were big, like this. And the reason is nobody knew what a book should look like. The only thing they had as a model were these old manuscripts. 50 years later, Aldus, who was a printer in Venice, his last name was not PageMaker. It was Aldus Manutius. And actually, his Italian name is Aldo, and I think of him as Aldo Manutio, because it sounds more friendly than Aldus Manutius. And he wanted to do a portable library around 1500 and went out in the streets of Venice measuring saddlebags to see how big the books should be if they were going to be portable. And the answer he came up with was the size book we use today as our main size book. And now you'll never forget that, because it's such a wonderful story that Aldus actually went out and did user-centered design to make his portable library. But in spite of people like Aldus and Erasmus understanding what the book was going to become, the actual printing revolution didn't happen until about 150 or maybe even 200 years later. If you look at it from the standpoint of the way the printing medium was used to argue, the rhetoric gradually changed to the rhetoric that we view as modern rhetoric for arguing about politics and about the real world and science. And all of this new way of expression and the new way of using the printing press was done by children, because 150 years later, nobody who was involved in the invention of the original technology was still alive. And the people who understood back then what the book was going to be had also died. Right? So the people who understood the great idea did understand it back then, but the large group of humanity actually had to grow up into it several generations over before the children actually found this thing. I think this is what's going to happen with computing, because we have a similar kind of thing. Sort of the millions of dollars thing is kind of mainframes owned only by institutions. And the desktop computer, the workstation, is kind of, the Gutenberg Bibles, by the way, cost about $60,000. 3 years of a clerk's wages. The Nuremberg Book Fair proclaimed them. And they were all marvelously similar, the advertisement said. They showed 24 of these books that were as similar as they could possibly be. So this is like a workstation here, and here's our little notebooks designed to be portable. And this is not hard to figure out because of Moore's law. But the thing that's hard to figure out is when are we going to get something that is equivalent in the large dimensions, so something closer to universal literacy. Only 1 person in 100 in Europe could read back here. 80 in 100 could read a little in here. Schools had developed to teach reading to everyone by here, reading and writing, thinking about the ideas in a new way, and so forth. So when you look back 40 years, you can see a lot of promising stuff that happened then. We'll talk about it a little bit because it's worthwhile thinking about how some of this great stuff got started. And then when commercialization happened, it kind of died away. This may be overly harsh. But if we take a look at one 40th anniversary, this happens to be the 40th anniversary of the funding of Project Mac. And Doug Engelbart's proposal to ARPA was done in '62, right before, so it was just starting to happen here. And Licklider, and this is a picture of him actually from that era, when he was the perceptual psychologist, went to Washington. They had some money left over from the space program as it went over to NASA, and they decided to give it to him to do with whatever he wanted. And he decided to try and deal with this idea that he'd had about man-machine symbiosis. And he wasn't the only one who had it. But he had a nice phrase. He said, "Not too many years, human brains and computing machines will be coupled together very tightly, and the resulting partnership will think as no human brain has ever thought." So if we look at where we are today, it just hasn't happened yet. It's happened in the sciences. The sciences, particularly the physical sciences, have been absolutely transformed by the computer. And scientists are thinking in ways that no scientist ever thought before because there are computers. But in general, this is not true. It has not happened yet. So let's look at a couple of the ARPA goals. Sorry. One of them is this notion of end-user computer literacy. And now last year was the actual, I'm fudging a little here, last year was the actual 40th anniversary of Sketchpad. But Ivan's thesis was signed in January '63, so I'm claiming something here. It was always worthwhile, I always contrived to find a way of playing this because it's worthwhile thinking about this period when we like to say there was only one personal computer, and that was when Ivan was on a machine that was much larger than this room from 3 to 6 o'clock every morning. So this machine did not even draw lines. And notice he's pointing to the segments here, and he's saying, now make everybody mutually perpendicular. And Sketchpad there just figured that out and made him a nice little flange. So continuous zooming and clipping on this first. This is the first actual window ever done. This display could only plot points, so Ivan had to write the line drawing routines as well. So there the constraint was parallelism, and now the constraint is collinearity. So he's using those solid lines as guidelines for drawing the dashes, and then he'll make the solid lines invisible. So about half the capacity of this huge Sage computer, the TX2, was used for doing the graphics. Okay, now he's got the hole in the flange. And the actual sheet of virtual paper he's drawing on is about 1/3 of a mile on a side. So it's a continuous zooming interface. This is why it was called Sketchpad. The idea was to just draw quickly an idea and then get the machine to clean up the drawings by telling it what the additional rules were. So he used the center of the cross pieces there for the center of the radius of the circle. And so when he tells the thing to become mutually perpendicular, that drags the circle and makes them a nice little rivet. And so Sketchpad is actually a continuous nonlinear constraint solver. So a little bit like a graphical spreadsheet many, many years before the spreadsheet, because it could do nonlinear problems like stresses and strains on bridges and so forth. So now he's got himself a little rivet there. And here's one of the first ideas this ever appeared in software, is the notion of making an instance. So this is an instance of that rivet, and you can rotate it and position it and scale it individually. So he's going to anchor it into the flange there. You can see that the success of Sketchpad led to a desire for nicer displays. And here's a very powerful idea. One of the first times ever in software is the idea of multiple instances. And then he notices, whoops, I've got that cross piece there. Let me go back to the master, which today we'd call a class. Let me make the cross pieces transparent. And now when I go out to my drawing, the instances have all felt that. So this is a true object-oriented software system. I believe the first real one in all important details. And it's a prototype-oriented system because when you make something, so he's got this rivet in the flange, he can make that into a class or a master. And now he's getting instances of that thing he just constructed. So this is dynamic object-oriented programming done by continuous problem solving. And I once asked Ivan, how could you possibly, in 1 year, have invented computer graphics, have invented object-oriented software, and done the first real-time problem solver? And he looked at me and said, well, I didn't know it was hard. So he had a tremendous advantage in that nothing was known about computer graphics. Nobody had really done it in any interesting way. And one of the wonderful things about his thesis, which, by the way, is available from MIT. If you get online and go to the Barton Library or one of the library services at MIT, you can get the PDF file for it. And it is astounding. I believe it is the closest thing to an act of a Newton in our field, in the sense of Newton's stuff was impressive in any age, and maybe most impressive from where we were before Newton to where we were after Newton. And so Ivan here, in one PhD thesis written in machine code on this huge ungainly machine, sort of gave an entire image of what it was like to be able to sit down and not just make pictures on a computer, but make things that were simulations. So this is, in many, many ways, everything certainly that I think I've been doing, and a lot of us have been kind of footnotes or fleshing out this incredible vision and realization. Unfortunately, Ivan is too restless to actually, he could do most unbelievable things in little 5-year periods, and he had to move on to something else. And those of us who followed him just simply lack his incredible talents. So it's actually hard to go out and buy a system today that will do all the things that Sketchpad could do back then. Kind of an interesting commentary. So another paradigmatic system is sort of almost the opposite, done exactly at the same time, was the original video game, Space War, done on the PDP-1. Here it is. If you ever programmed it, it's really one of the first machines that anybody would call a honey, because it was just right there. It was sweet. You could really make it do things, and it had one of the early graphics displays from DEC on it. And one of the first things they did on it was one of the first graphics text editors, which they called expensive typewriter, because it was basically a typewriter, except it cost $110,000 or so. And then pretty quickly, Steve Russell had been reading the Doc Smith Lensman series and decided to take a shot at trying to do that. And he came up with something like this. And this is a kind of a recreation of it, but the basic idea is you got F equals ma going, and so when you try and steer the thing, you have the problem is you already have quite a bit of velocity built up, and so if you want to stop this thing, you have to point him away and try and kill off his velocity. So it's quite interesting and challenging to use even before they put a sun in there with a gravitational field that made it even more interesting. So now, Space War is one of those things that was so simple, so doable on a computer that pretty much every computer that had a graphics display on it, somebody would sit down and figure out a way to do Space War. And one of the most important things about it, it also used this object idea, as you wanted to have not just one spaceship, but a spaceship for each person playing it. So it had many of the interesting elements of what we think of as computer graphics today. And it's fun. Okay, so another part of the ARPA dream from way back was the idea of being able to do group collaborations. And this happened in two forms, which later got combined. One was this desire to do the intergalactic network, as Lick called it back then. And from Doug Engelbart's proposals about boosting the combined intelligence of groups. And so it just happens to be the 35th anniversary of the greatest demo that was ever given, actually a little bit later in the year, right, Bill? So if you don't, everybody here must know Bill English, but Bill, raise your hand, please, because everybody's heard of Doug Engelbart, but Bill was the guy who made all the stuff work. So he was the partner, he was the co-inventor of the mouse, which was invented in '64. And this picture here is a picture that could have been taken yesterday at somebody sitting at their desk, but it goes all the way back to the '60s. So this is kind of the birth of personal computing, the way I look at it. Whoops, and do we have sound? Somebody giving me sound from this thing?
Let me look just that low.
So let me stop this for a second. This is one of the advantages here of having a system where the authoring is always on, is I can just rewind this guy. Let me just move him up to about here. Start him again.
So I can say, all right, I'd like to go to produce, but I'd like to go to produce, they get big, I'd like to say one branch only, and let me look just that low, and I see it. Oh, I can say, I'd like to see one line only. I can see it. But there's another thing I can do. There's a root I said I have here. So here, I'm afraid I'll need a different picture of the view. So here's what I drew with a picture drawing capability here. It's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that, And oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, very interesting. All right. Market can do things if I want to just say, I'd like to interchange produce and canned materials. Bingo. And they're all numbered rightly if I care to look. Interchanging them very quickly. Cans are going to get interchanged with produce. They do it and all gets renumbered.
So one of the nice reasons for showing this is you get a nice, this is from the 68 demo in San Francisco that I was very happy to be there. It was one of the, run like a military campaign. Nothing was left to chance, right, Bill? It was the most incredible thing you've ever seen. And that thing on the puny little thing there was bigger than this whole screen. It was just this huge thing done by one of the first light valves that was pretty much using an atomic bomb as a light source. Huge, big situation display. But one of the reasons I show that is the computer was actually down in Menlo Park while Engelbart was giving this demo up in San Francisco. And we'll talk about that in a second. But if you look at the response on this system, you'll notice the response was sub-second on all important interactions. And I have to tell you, the computer this was done on was about a half a MIP, 192K bytes, and was time-shared. So Doug was not the only user on this machine. Think about that for just a second, and think about what we don't get off these several hundred MIP machines. We do not get sub-second response. So how could these guys have possibly gotten sub-second response? Anybody got a theory? Okay. That's a necessary but not a sufficient condition. Who's got a more close order theory? Okay, I'll tell you why. The reason is because they wanted to get sub-second response. They were not going to be settled for anything less than sub-second response. They worked their asses off to get sub-second response because it was part of their image of what it meant to fly. That was one of the metaphors, to fly through n-dimensional thought vectors and concept space. So this was a conception, a grand conception, about what it meant to have a corpus of knowledge that was useful to other people, and also an understanding that in any retrieval operation you're doing, you're spending most of your time rejecting. So the only way you can make something like this work, whether you're browsing or any kind of searching, is you have to reject quickly. So they had this thing set up. It was just incredible. We could go on and on about it, but it's worthwhile when you're thinking about the future of software. You don't have to go much past this in 1968 to make your first list of 15 criteria for what you should do and what you shouldn't do, because they just really, really went after it. And the next part of it is perhaps even more interesting and was part of the original conception as well. So check this out.
Now, computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it, and I can see your face, and we can talk.
So Bill is down
let's
in
do
Menlo
some
Park.
collaborating.
Go off to a directive file and see what the directive is to get Roman numeral page numbers. I'm into the file now. Here's the first level of the hierarchy. Let's open up page formatting.
This is Engelbart's
Look,
bug
we
over
want
here.
page numbering, so we'll open that up. We find, yes, here it is, Roman numerals. We find out the directive. Yep, your bug's right on it already, Doug. Here's the directive we want. So we've worked down quite a way into a hierarchy, as you can see.
Okay, so another part of this conception was that through every part of the system, not as a feature added on from the outside, but to be able to do immersive collaboration of various forms. And this was a demo of it, and they even had their meetings. When they had a meeting in the same room, they had the consoles down in these sort of circular table arrangements that they had, so that they were actually sharing the context and they were using this as a shareable blackboard back then. So one of the nice things is you can get videos of these demos. There's a lot of stuff written about it, and if you're interested in any kind of improving group process, thinking about what criteria are for starting, you have to start here. It's because most of us aren't as smart as these guys were. And the software that we are given today proves it, because it was made by people who never looked at this stuff, never understood it. So another thing that ARPA was thinking about was kind of a form. We saw one form of what the computer environment was going to be like. Here's another one from RAND. It was done about the same time. And it superficially doesn't look that similar, but it actually is remarkable in the points of similarity it has with the Engelbart system, come at from a completely different point of view, which is from the standpoint of the end users that they dealt with at RAND Corporation. It's called Grail, and it's one of those amazing coincidences that both the tablet and the mouse were invented in the same year. So I don't know whether you knew that, Bill, but so Tom Ellis did this, and these tablets were actually kind of like a sign that you were a real graphics person back then, because they cost $18,000 in 1968 dollars, which is like $100,000 today to get one. They're made by hand. So there are probably less than 50 of them made in total. So take a look at this end user system.
First, we erase a flow arrow, then move the connector out of the way so that we may draw a box in its place.
So it recognizes he wants a box and makes one. Now it's recognizing his handwriting.
The printing in the box is
Compare that
being
with
used
graffiti,
as
by the way.
commentary only in this case. The box is slightly too large, so we may change its size.
Where modern window control came from, literally.
Then draw a flow from the connector to the box. Attach a decision element to the box and draw a flow from it to scan. We then erase the flow arrows attached to the process post new area and move the box to a new position. This allows us to draw a new box.
So you get it? So, question that one could reasonably ask in the year 2003 is, why the heck can't we do that on our PDAs? And the answer is that nobody who's making PDAs has the faintest idea that this would even be neat to do. They just can't imagine that it's anything but a little tapping thing, and it is truly amazing to me that graffiti is not as good as this recognizer was back then. And in fact, this recognizer was published in a paper in 1966 by Gabe Groner for just anybody who wanted to know how to do a single-stroke, almost perfect character recognizer. It's been in the literature since 1966. But the people who did the things today absolutely did not. We're not going to go back and read anything that those old people did. Hey, we're just as good, if not better. So this is, to me, the real difficulty with getting software into the future is that software can't even use the past. And so we basically have millions of people now who are programmers, and by the law of the bell curve, most of them are average or worse. In fact, if you think about what a bell curve is, 83% are C's or worse. So if you throw a bell curve on programmers, and you basically have a tyranny of the majority that winds up, full of sound and fury, signifying nothing. So this is a huge, huge problem. So one of the biggest first things that we could do to get ahead in software is to at least start with best practice. And the other thing that was nice about this recognizer, it was only about 8K of code because it ran on a really small machine. That is, the machine was an IBM 360 Model 44. But it was pretty tiny from the standpoint of bits and bytes. Okay, and then sort of a more indirect thing that ARPA had a huge part in was in trying to get real computer science and engineering invented. Now, I claim this hasn't really happened very well yet, but there are some really interesting stabs at it. My favorite one, what I think of as the best thing ever done having to do with programming language, was McCarthy's invention of Lisp. And it was done kind of in a typical way that these things get done, is that McCarthy was basically a mathematician, and so he was able to do this when he was thinking about a universal way of doing computing. This is kind of the Maxwell's equations of programming. So it's the bottom half of page 13 in the Lisp 1.5 manual, and pretty much everything that is good about programming is in those few lines. So it really has a lot of the Maxwell's equations. And then Steve Russell, again, the guy who did Space War, was the person who coded this up and made it into a real language called Lisp. And then many other people worked with it. That happened a few years earlier, but this year, and I just sent an email to Peter Deutsch yesterday to confirm that this is indeed the 40th anniversary of a truly remarkable version of this, which was the first interactive Lisp on a standalone machine, and it was also its own operating system. It was done by Peter when he was only 16 years old. So if you've ever puzzled through trying to understand the Lisp eval, imagine a 16-year-old boy being able to understand it and writing one of the most beautiful machine code programs ever for this machine. And many of the things that we wound up doing after this were based on the fact that this stuff had been done. Tiny little machine, actually ran in what was called a 4-core machine, which is 4,000 18-bit words. So it's a little over 8K, 9K or so. So the interpreter was about 2K, and you had the rest for doing computing in. Now for me, my background is in math and biology, and my first collision with this stuff was in running into Sketchpad and then Simula, seeing the similarity to biological cells as a universal building block and thinking up the idea of dynamic objects. Then we tried this as an operating system on this little machine called the Flex machine, early desktop machine. I later saw this wonderful Grail system, and the same year I saw an early flat panel display at the University of Illinois. So we started thinking about the prospect of putting the transistors in this machine on the back of one of these displays so you could do this. And that same year of '68, I saw Seymour Papert, who had had a tremendous insight involving children that certain really important forms of advanced mathematics, particular vector differential geometry, was akin to the child's own way of thinking about itself in the world. So the child is the zero, wherever the child goes, it's at the center of the universe, the narcissistic coordinate system. And that, if you know differential geometry, you know that's the coordinate system that differential geometry uses. It's always, what is the geometry like from where you are? And so, for instance, a circle is just go a little, turn a little over and over again. You don't need any x squared plus y squared equals r squared or any of that stuff. So when I saw that, it blew my mind completely, and that got me thinking about this little computer for children. And my image of it was 12 and 13-year-olds here would actually sit down and program their own game of Space War learn about Newtonian dynamics in the process and have fun playing. And those of us who were around a long time ago will remember, and the Computer Museum has it parked outside its old building, is the old SRI bread truck. How many people remember the mobile radio, packet radio stuff? Yeah, John Schock does. So it's this, I think it was a Ford Econoline van or something. It was packed full of stuff. And one of the frivolous things that happened back then was one of the first emails ever sent from the beer joint called Rosati's up in the hill. They drove this Econoline van up there. They had not even a line of sight, I guess, but it was packet switching to SRI and then into the ARPANET into Washington. Meanwhile, they're swizzling down beer with their terminal on one of the outside Rosati's picnic tables. So we knew that wireless computing was going to come, and this kind of packaged up the idealizations of all of this stuff into this one idea I called the Dynabook. And so if you take this ARPA dream, it took shape for me when children came into the picture, because I really didn't know how to design for adults. I wasn't very adult myself. I didn't have any real contact with that world, but improving the child's condition for learning was something that really appealed to me, so I got very interested in it. And I have to thank Bill English once more. It's great that Bill is here because I rarely get a chance to thank him in public, but Bill actually took me under his wing when we started here at Xerox PARC a long time ago. And one of the things he said to me is, Alan, maybe you should write a budget. And I'm afraid I really did say to Bill, Bill, what's a budget? Remember that, Bill? And he said, well, you put this number here and you put this number here. So this is actually the 30th anniversary of Chuck Thacker's Alto. Here it is. And so that was a real milestone. It went along with a whole bunch of other stuff that we did. And historically, it had an interesting parallel with the PDP-1 Lisp thing, because it was the strength of what McCarthy had done. Because I'm basically a mathematician, not a programmer. I program a little bit, but I don't consider myself a programmer. But I felt I could do the same thing for an object-oriented language that McCarthy had done for Lisp. And this is one version of it. And Dan Ingalls, who is right over here, Dan, raise your hand. So Dan was the reality guy. He took this little paper thing and made it into a succession of Smalltalks that live to this day. And Chuck fashioned this first bitmap machine. And from our standpoint, what we're really trying to do was to get enough machines built so we could take them down into schools and start working on it. This is Adele Goldberg here. And now up to the present, I'm just going to show you a few of the kinds of things that we've been doing. So Squeak is kind of an outgrowth of some of the stuff that we did at Xerox PARC. And we don't think of systems like this as goals. It's hard to define, but it's relatively easy to define computer systems as vehicles or media. So you sit down because you're basically trying to make models in it, and you get ideas for new kinds of models, and so you have to use the modeling material to make the different kinds of modeling material to make the models and so forth. So this system is a wide spectrum system, and it's been implemented on many, many different kinds of platforms, bit identically. I'm going to explain a little bit of that because I think it's very, very important for future software, especially having to do with the internet. It's also of interest because it was basically done by this small group of people here. Here's Dan Ingalls again, Scott Wallace, Ted Kaler, John Maloney, and Andreas Raab. So it's an example of a system that involves its own operating system and many, many things that we think of as applications done by a very small number of people rather than the hundreds of people that you think of needing it. So there's interesting questions about, well, how was this actually possible? It has a very flexible object system. So if we take this is kind of a cute little demo here. If you take a paragraph doing word wrap, and you're in a real object system, then you can just let those guys wander around here. And if you think about what do they have to actually do, they kind of have to follow the leader. Right? I can get them to go faster. And the algorithm we usually think of is kind of the one that is done between frame times. So it's actually doing the same thing there, but between frame times, it looks like it's happening instantly. That is a very easy way of programming, because it's basically just 4 little rules to do it. There's many kinds of media in here. I'll show you just one other thing here. And so we live in a world of applications. But if you think about it, applications are one of the worst ideas anybody had. And we thought we'd gotten rid of them here at Park in the 70s. Because applications kind of draw a barrier around your ability to do things. What you really want is to gather the resources that you need to you and make the things that you want out of them. So for instance, one of the ways of thinking of desktop publishing is that it's just graphics done right? Because you basically want to be able to make almost any kind of graphic construction on the screen. You want it to be able to react to things, and you want the elements to be not confined in the bounds of an application, but be part of something else. So you should be able to have primary and secondary reactions. So here I'm drawing through text, just as you would expect, but I should also be able to hop the fence here and, for instance, drag this guy out like this, but I should be able to do this without destroying. So you see if I'm scrolling here, it's scrolling there and flowing through. So these objects interact with each other to the extent that they need to, but no more so. And you kind of get desktop publishing for free, or any kind of media composition. And actually, one other thing I should show you here, as long as we're talking about this, is an idea that I spent 12 years at Apple intermittently trying to get them to adopt, which is the idea of unlimited desktops. And Smalltalk at Xerox PARC had this, and the Squeak system here has this. And what I mean by that is that each time I decide I want to do something, I really want a separate work area to work on, and I like these work areas to persist over time. And we've been looking at them. So there's no separate presentation thing. There's nothing like PostScript here. I mean, nothing like PowerPoint. So if we look at the projects that are in this guy here, we can see the presentation that I've given so far. Right? Here's where we are right now. Here's the next thing I'm going to show, and I decided I'd really rather show this thing. And each talk that I give is a sorting of the projects that I have. So the idea is you never have to go to anything weaker like PowerPoint to give a presentation. You just link up the various things that you've been working on and show them. And these things are also the things we ship around the web instead of web pages. Okay, so just a word about how the porting is done. It's kind of cute. So here's the thing that I think is actually known but is not well dealt with in software, and that is that for decades, software has been specified using paper documents. People have tried to implement to those paper documents, and then they've tried to run a benchmark suite of some kind to validate the implementation. And to my knowledge, it has never succeeded in producing compatible implementations across platforms. Fortran is famous for the exceptions. And even C is not exactly the same across platforms. So that is really a shame. So a different way of doing it, though, is to make a model of your kernel that can be debugged. So it's not a paper model. So when we decided to do Squeak, there had been some experience in doing various kinds of Smalltalks at Xerox PARC and afterwards. So the idea was to found an old Mac that would run an old Apple version of Smalltalk, and we'd written a book 20 years ago, 20th anniversary of this book now. And this book had in it, among other things, it had the VM of Smalltalk written in itself. So if you type that in and get it running, you have a simulator of the VM. Then you could treat that simulator as the spec and say, okay, that's the only validation and specification of the system that we're going to have. And we'll debug this, and when we get it running, we will have the definition of the VM that we're hoping for. Now, of course, this doesn't do you any good because it's running glacially slowly. So the next thing you have to do is write a translator of that. And this work was primarily, for Squeak, was primarily done by Dan Ingalls and John Maloney. A translator, and this translator should, without changing the meaning of what the simulation does, translate it into a lower level form that can be put on another machine. Like we chose a subset of C as the lower level form to go for a target, the subset of C that tries to be compatible across platforms. So all of a sudden now you have a PowerPC VM, and this top stuff is machine independent. So all of a sudden we were now off the old Mac and onto the PowerPC. And since it contains all of this stuff, you can use it to improve itself. About a month and a half after we put it out on the net, a guy in Germany we'd never heard of before sent us a version for all the Intel PCs, and that's what we run today. And it now runs on 30 platforms, bit identically. Because the key idea here is the debugging of this complex thing and then having a mathematically sound translation that preserves the actual meaning. So in many respects, you can think of this as an old technology or a new technology, but very few people are doing this today, even though they're trying to run on many different platforms on the internet. Now I'll show you the relationship of Squeak. So there's this nice malleable stuff called CPU and memory. And then there are bad de facto standards called operating systems that take away most of the degrees of freedom. And the internet with TCP/IP is really great. And then there's a really bad de facto standard called the World Wide Web. Takes away most of the things that you want to do. So we actually, when we're running on a machine, like I'm running on a Mac here and we have a couple of different PCs here, we actually have our own operating system, but we contact the existing operating system at a single point, which equals about 1,000 lines of code, because we have to share the display if we want to do this without killing the existing operating system. But all of our own tools are inside of Squeak, and these go portable with the rest of the stuff. And the same thing with our own socket system for handling the internet. So this gives you a completely portable system that can go across a wide variety of platforms and usually takes just a week or two at the most to do the port. Something to think about for the future of software. Okay, so let's take a look at the present. I found doing these things, just showing some of the kids' stuff, makes most of the points in a way that's easy to understand. Nice thing about working with kids is when you give them something, they feel quite free to reject it. It's hard doing tests with adults and companies because adults have been trained for 25 years to take shit. for money. But most kids haven't learned that yet. So what the kids really want to do is have some fun. So like a fun project for them is to design a car that they can learn how to drive, paint it. It's like a 10-year-old kid here. Put in some nice little specular reflections that we learned how to do at Disney. And we found that both boys and girls love to put on big, powerful off-road tires on their vehicles. So their vehicles wind up looking a lot like this usually. And we got a little graphic object. And in this system, and this is an insight that goes back a long ways to the days of Xerox PARC, was I think after one of our beer busts at the Black Forest or something, I was blearily looking at the screen in my office, and I realized that to an end user, there were only smart rectangles floating around on the screen. All of the crap that we had underneath, all of the inheritance, all of the other stuff was totally invisible to a naive end user. It was just smart rectangles. And if you start thinking that way, you start thinking about, gee, what I really want to have is universal objects that can wear costumes. And I'll give them a little bit of idiosyncratic behavior and try and build my system out of that. So here's our little car. And it's a graphic object, but it has another view of it, which is symbolic. I'll call this car. The kids like this, and we're trying to teach them math, so we want to get them interested in this. So, for example, if we look at this property called car's heading and start it counting up, car turns. If we turn the car, we see that heading changing. Here's a behavioral property, forward, ba-ding, ba-ding, ba-ding. Turn, ba-ding, ba-ding. Make a script, just drag out a tile. Hit the clock, start it running. And of course I can steer by just changing the numbers here. So a good one is 0, which car goes straight. Negative numbers, it turns the other way. But that's not really like driving a car. So we say, okay, make yourself a steering wheel. I always do a blue one. So it's just another little costume on one of these guys. Look inside of it. Call it wheel. It's got a heading. If you look at that number there, on heading it goes positive and negatives. I turn the wheel. Positive and negative numbers here influence the car. So that's an invitation to pick up the name of the numbers coming out of the wheel. Just drop them in there. And I should be able to control the car now. So it's sort of, for the kids, it's one step learning about what a variable actually is. It's generally one of the harder concepts for kids to grok. But it's very easy here because it's operationally in their space. And the system is just recompiling and recompiling and recompiling as we go, every time we make a change. So these scripts actually run as fast as the underlying Squeak scripts. They are the underlying scripts. So you can do very fast things, as we'll see in a little bit. Okay? So once they've done some of that stuff, we can investigate the real world using our ability to make models now. Sound, please. Keep the sound on.
Both hands. Oh, do not pay any attention to what anybody else is doing.
Who's got the apple?
That's the janitor.
What do you get? What'd you get?
They try and use stopwatches.
The 0.99 seconds.
Together. So put sponge ball.
Okay. I think we should do the shot put and the sponge ball because they're two totally different weights. And if you drop them at the same time, maybe they'll drop at the same speed.
Drop.
So So the average of Galileos per class is usually about 1 for 30 kids or so. So this little girl cut right to the chase. She realized the stopwatches were bad because you couldn't tell when the janitor was dropping. It's hard to, the whole thing takes about a second or so. And so she just thought, well, all we have to do is listen when they hit. If we can hear 2 hits, then they're falling at a different rate if we hear 1 hit. So this is Galileo's insight back when it was hard to time things. So children can actually think about this stuff operationally very well. And as we'll see in a second, they can do better than most college students. So the way to actually investigate this is to take a video of the dropping ball here. And hard to see what's going on by looking at the video, but these frames are actually part of the objects that we can do things to. So we can just pull frames out. We can stack up every 5th frame here. We can stack them up vertically. And we can start measuring them. So one of the ways of measuring these is to make the height of a rectangle go from the bottom of the ball in one frame to the bottom of the ball in the next frame. And that vertical drop is actually the velocity, because it's the distance traveled in unit time. You can see the velocity is increasing. We'd like to know how the velocity is increasing here. I'm doing this a little bit too quickly, but so one of the ways we can get a qualitative look at it is simply by stacking these guys up. Galileo had a very interesting way of doing this himself. And if we look at this, we see, oh, the change in velocity looks constant. Change in velocity is acceleration. So it looks like constant acceleration. So the little script that they write looks like this. They make a simulated ball and have a variable called speed, and they say, let's increase the speed by -5, a constant each time, and then let's change the ball's position by that speed. All right, so that's a second-order differential equation done by 11-year-olds. And we'll let Tyrone tell you how he did his.
And to make sure that I was
Sound,
doing
please.
it just right, I got a magnifier, which would help me figure out if the size was just right. After I'd done that, I would go and click on the little basic category button, and then a little menu would pop up, and one of the categories would be geometry, so I click on that. And here it has many things that have to do with the size and shape of the rectangle. So I would see what the height is. And I kept going along the process until I had them all lined up with their height. I subtracted the smaller one's height from the bigger one to see if there was a kind of pattern anywhere that could help me, and my best guess worked. So in order to show that it was working, I decided to leave a dot copy so that it would show that the ball was going at the exact
So he's
right
leaving a
speed
little
and
cookie
acceleration.
behind to show that it matches up with where the thing is in the frame. Another one that the kids did is running the movie against their simulation, like this, to show that they've got the thing nailed. Is that cool? So if you know anything about this, this is one of the most studied difficulties that college students have in science. There are literally hundreds of papers that give every kind of statistic you could ever hope for. But the most interesting one is that 70% of college students who encounter this in college can conclusively prove that they don't understand it. So this is one of these point of views is worth 80 IQ points thing. Because the form of the math that's used in college is not the best kind of math. This is a really great kind of math for this because it's a state space math. It gets rid of all the multiplications and makes them into additions because you've got the looping adding up the additions into the multiplications that are in the standard formulas. And it's just a simple 2-stage, if you are old enough, digital differential analyzer that does this stuff, and it's just right there. And immediately the kids use it to start doing things. They can shove things off cliffs. They can fire water balloons. They can make a lunar lander game. So here's the little two-stage thing. Drops the spaceship down there. So gravity eats velocity. The motor of the spaceship produces velocity. This little script makes a flame appear when the motor is on. This is the one that crashes you if you're going too fast. So a lunar lander game looks like this. So I can toss the thing up on its jet. I can ease it down. People used to spend money for that game. And of course, in the spirit of this thing, have to do Space War. And again, we have a way of doing the sketchpad kind of prototyping. So here's a spaceship with its acceleration variable, because now we're not worrying about just vertical stuff. We have to worry about vectors, velocity variable, the joystick, and so forth. And we want to be able to make several of them. We can just copy these by using the green copy button here. Put these spaceships into the universe here. We can differentiate, say, this guy by giving it a different color. And we can start them both going. All right, so this is kind of what I was talking about. This is the program that you have to write in order to do this, and that is the only program that you have to do. So the interesting thing about most software is that the mathematics, you can think about what the actual prime relationships are of what you're trying to do. You realize they're tiny almost always compared to the code that you wind up writing. There are many different reasons for this, and we should talk about them a bit. Right now, I just want to move you through a few more examples and then show you some edge-of-the-art stuff we've been working on, and then have some time for questions. So here's a fun program now thinking about feedback done by these two 11-year-old girls. The idea is have the car be able to stay on the middle of the road as a robot car. And if you look at this little script, you can see when the sensor is touching the middle of the road color, it's going to go forward and no other condition. When it's touching the green curb, it's going to turn one way, and when it's touching the yellow curb, it's going to turn the other way. So they analyze this into 3 separate cases. And you can see it's quite smart, because when it runs into a sharp turn, it really doesn't go forward. It just turns its way around. And when questioned, the girls said that, yes, of course this will work even if we don't draw the lanes well, because the +4 and the -4 will cancel each other out. And so even if all 3 of these guys are firing, it'll work just fine. This is the kind of mathematics that you're hoping children are actually able to do. Okay, here's another example. Remember I said these things have costumes. So here's a bunch of objects drawn by Sam, and he's increasing the cursor by 1 over and over again so we can see it going through there, and then he's telling this guy to look like the costume that's down here. You can learn a little bit about rates by putting, like, for instance, a 2 in here. 1.5 is interesting. 0.5. And the kids realize immediately, well, gee, that's all a movie is. Movie player is just 2 lines of this stuff. Then there's something that they didn't suspect, that when you say something into a microphone, the system gives it back to you as a bunch of little rectangles in one of these very same holder guys here. And here's a cursor. When we move the cursor, we have a little program that's going to move the speaker This graphic speaker here is actually connected to the real speaker in the machine. So if we turn this on, as the cursor goes by, we're reading the numbers here and we're animating this thing. You might say, well, why can't I hear it? And the answer is it's going way too slow. But this stuff runs as fast as the adult stuff, so I can actually speed it up by a factor of 10,000. Tom. And I can play the same games. What if I put a 2 in here? 0.5. And 1.2. Tom. And say 1.5. So the children very quickly realize that the $300 they just talked their parents out of for a synthesizer is actually paying for 2 lines of code and some recordings. And they quickly just make buttons. And the button has the action of putting the magic number into a variable and just playing this thing over again. They have a little synthesizer. So the point here, I'm not trying to get you interested. Of course, I am trying to get you interested in the kids' stuff because not enough adults realize that the kids are going to be the ones who invent this stuff. The last 20 years have proved that adults are hopeless at inventing this stuff. So we should pay more attention to the kids. But what I'm trying to show you here is that the models, what you might think of as the discrete mathematical models for things that are considered to be very complicated phenomena in programs, are actually extremely simple. So if you actually make a software system that's able to deal with those models directly and abstracts into a different place the optimizations, you get a very, very powerful, very, very simple way of programming. Okay, just a couple more. If we take the feedback stuff and apply it to looking for shades of lightness and darkness, we can do a salmon swimming upstream. What it does is it circles until it finds something darker. So it's continuously acquiring and losing. And it only has one little piece of memory from the last time it looked in the water to get it to follow this gradient. Clownfish does the same thing with the circular gradient from the sea anemone. Okay, and once you have done that, then you can use these ideas that we've adapted from Star Logo, which is this is like a zillion little salmon, but they're ants. The ants wander around randomly. When they find the food, they pick up a particle, go to the nest, and they leave a scent trail behind. And so there are about 10,000 patches computing in parallel here, diffusing the pheromones and evaporating them. And this is kind of interesting because you see very quickly a large percentage of the ants have been organized by this loose coupling. This is a loose coupling architecture. Even though the ants aren't communicating directly with each other. So here's one where they've run out of food, but there's still scent. So it's kind of like Wall Street. So that's kind of interesting. Learned about epidemics. If you take the particles and apply gravity to them, you get buoyancy. This is truly beautiful little thing. So you have thousands of particles here. And if you ever wondered where does the upward force comes from that floats things, it comes from the force of gravity on a liquid or a gas that's confined. If you don't confine it, it just spreads out. So it's the putting it into something that has walls of some kind, including a circular, spherical Earth, that makes it impossible for the particles to spread out sideways. They start piling up, and they start exerting an upward force that's proportional to how many things that are piled on top of them. And you get this model very, very nicely. And we can change the mass of the sphere here, make it 100 times more massive. So I'll change this to 1,000. And actually, it's not going to sink all. Once it gets into equilibrium, it'll still be buoyed up a little bit, because it's not quite massive enough to sink all the way to the bottom. And if I turn gravity off, I get another interesting thing, which is when it stabilizes, I get Brownian motion, and we're still less than 100 years away from Einstein's original paper, which was written in 1905. Back in those days, they could only see the blue guys. So one of the best arguments for the existence of atoms was Einstein showing the kinetic theory of heat on small particles moving around would cause larger particles to move in the way that was observed. So it's a perfect way of actually understanding this stuff. Okay, so now we're going to look at some collaborative stuff. I'm going to go to so here's where I want to Booth switch over to this guy. Okay. So oh, it just wasn't showing up.
Yeah, it won't switch when it's
Okay. Okay, just a slight pause here. So I'll tell you a little bit about the problem, which is that when the internet was worked on, it was trying to solve an n-squared problem, and which was how to be able to get any node to communicate with any other node without having to make the crossbar switch in between. So that was done by a peer-peer, end-to-end way of doing things. And one of the problems with that solution was that it, yeah, you can connect me up too. One of the problems with that solution was that it made it very difficult to do what Engelbart had shown us how to do in the 60s, which is to do immersive collaboration. Because the problem is that there are, for n people on a network, there are 2 to the n subgroups, and you really can't allocate a server, as Engelbart's group was using, to solve this problem. So this is a catastrophic exponential that you have to deal with. So various people, including Dave Reed, years ago, started thinking about how could you do a peer-peer solution to this, which gave you the equivalent of something like EverQuest, but without having any central server at all. And we'll talk a little bit about the solution. The solution is basically you have a distributed replication of objects that has real-time transactions over a slow network. And we'll sort of give you a sense of what this is. Maybe we could dim the lights a little bit. And this is my friend Dave Smith, who's the guy who did the original first 3D game on a PC a long time ago, and Virtus Walkthrough, and many other kinds of things. And this system, which is called Croquet, was basically done by 3 people with a little kibitzing from me: Dave Smith, Andreas Raab, and David Reed. And Dave, why don't you?
Great.
So I'll be your slave here.
Am I on? Can you hear me? Can we turn me on somehow? Just do a switch here. Hello? That's okay. You're on. Oh, good. Croquet, as Alan said, is a collaboration environment. What you're looking at right now is essentially 2D display, but what you're really looking at is not what you think you're looking at. You back away from this. And I'll back away from mine. So Alan's the white rabbit, and I'm Alice. And if you look, I am the guy on the right-hand side. Alan's the one on the left.
Okay. Hello, hello. Sounds the same to me. Oh, there it goes. Wow. All right, so I'm going to go over here and show off a few things.
Yeah, I'm going to follow, most of the time here, I'm going to follow and see what Alice does.
This is a mirror, so I'm actually looking at myself and the white rabbit standing behind me, but it's a mirror that can move. It's a window floating in space. I can resize it. I can pick it up and move it around. Just like you'd expect I should be able to, right? There's nothing special about it. In fact, this is a portal into the current space that we're in.
In fact, I can grab it too.
So he grabbed it over there. So essentially, what's nice about it is any activity can be done by one guy, can be done by any person. So these are essentially objects that, you know, are exhibiting a certain set of behaviors, but we can use those objects in any way we want to. And any person can use them that way. Here's another object, this little pyramid. This is actually a Sierpinski pyramid. So I can actually modify its depth. I'm sorry?
Oh, yeah.
Yeah.
That's
easy, actually.
Yeah,
you do that all the time.
Right. That's a good one to ask. I can modify this thing also. Give it.
But essentially, it's totally.
That's me.
Right. Another thing over here is Alan again, and just putting a little bit of a, just so there's no distinction between 2D and 3D.
The first accurate rendering of my actual state of mind.
Right. And now we're going to go into another portal, but this time into a portal into a different space besides the one we're actually in. This is actually a little a Martian landscape. Notice as I spin this around, I can look around. It's like picking up a shoebox and looking around inside of it. Now, Alan's going to watch me walk into it, so you pay attention kind of to both of those. What's going to happen is this is actually...
Think of this as a hyperlink on the net, by the way.
Exactly. This is like a web page, but better. So I just dropped in. Do you see? I'm inside that world. If I turn around now and I watch Alan come in, there he is. Okay, it's a door. Over here we have a little robot that's in both of our spaces. And what I'm going to do...
I'm going to get up on the rock here so I can see you.
...is have it start moving around. So I'm controlling and giving it a little bit of a velocity. And I can turn it. It's kind of like the car that Alan showed.
See, it's got inverse kinematics.
Yeah, notice the wheels are following the terrain, which I find very cool. And I can attach myself to that frame, or I can drive it from behind. So I'm literally like sitting right behind the thing and driving it around Mars. Actually, yes, let me show you that. I can get on it. Now, Alan should be able to see me. Now, how cool is that? All right. I'll get on again. There we go. Something's, I keep hitting something. No, I should be able to stay on it. I'm not, but that's all right. Who cares? It should work, and we'll show you something in a little bit that illustrates that better. So, next thing is finding a way out of here. Oh, there's. By the way, this is just another one of those windows. This is identical to the ones that we saw before, so we can move this around just like we did, and we jump out. Here's another portal to yet another space. We'll jump into this one.
I'll go the other way.
And what we're going to see over here is yet another portal into this world. What we have going on here is this neat little flag. Now, this is actually the first thing I ever did in Squeak. This is actually a full mesh
physics it's a mass spring model. And just to prove it that this isn't the canned simulation, I'm going to release the top of the flag. So
I'll jump in here so I can watch you doing this.
And then I'm going to start pulling it back like it's a rope back onto the thing. Now
This is a lot like the particle system stuff, except the particles are constrained.
Now I'm actually standing on that little.
So I can grab it here and give you a little toss.
So I'm on the little carousel now, spinning around, as you can see. What's really neat about that to me is that he's actually controlling my position in the world remotely. I mean, it's literally. It's like he's changing my state in a dramatic way. It's just a fundamental thing that's just really fun, but dizzying. Over here we have a little tribute to Scott Fisher and Warren Robinette, the little escalator. And this escalator actually works. I can get on it, no hands, look, I'm being picked up. And back up. This is where we started, if you recall. Let me close this guy. What's next? Do we go to
I'm going to close this guy.
Okay. Should we go
Let's
to
see, we should go to the vivarium world.
Oh, that's right. Geez, I knew there was something I forgot. This is our good friend Andreas Raub, one of the co-creators of the system. And what we have here is an underwater land. Now, what's interesting about this is when I jump into this, I actually turned into a fish, but what we're going to do is watch Alan do the same.
Whoops.
You went to the wrong place.
I'm always doing that.
Now, watch as you'll see Alan come through. See him there? Oops, he turned into a fish. Now what we're going to do is populate this. There's a few fish swimming around, but we'd like our own.
Now go up closer.
Up here?
Yeah, go up there.
Yeah. Well, if I go too close, the fish will
Okay.
show up under the ground. So what I'm going to do is draw one. And literally, this is a little paint package. And I'm just going to do a quick and dirty fish here.
So this is derived from a master's thesis by Takeo Igarashi, who's now a professor at University of Tokyo. It was originally called Teddy. You can look it up on the net. It's really very cool. This is one more advanced version of it.
So what I did was I drew a quick and dirty model of a fish, which any child could and should be able to do. But guess what? He's inflated. And what you'll see in just a second, if he's not already there, there he is, both sides. So essentially we're able to collaborate.
I can pick him up.
And so Alan's moving him around. So Alan's going to make some seaweed for us.
I should make some seaweed. So this is a real challenge for this thing that none of us ever thought of, but I think it was Dave's, 5-year-old son or something, thought about making something like this. And this, if you know what this algorithm does, this is kind of frightening. Because the algorithm has to figure out the major and minor axes of things. And then once having done that, it uses that as a way of intuiting what the 3D shape is going to be. So this is going to compute for a little bit.
Yeah.
Figuring out what the 3D. I'm always amazed when this that this works. There it is.
And there it is.
There it is.
Isn't that neat? I just think that's one of the, what we got is the simplest 3D modeling tool ever built, which is just, for me, just a joy. This thing is so much fun, you have no idea. When you start building and start making starfish, you start making...
Yeah, this stuff is scriptable just the way the 2D world is. Okay, let's chug our way out.
And of course, when we go out, if you watch me, we return to our normal forms.
Okay, there you are. Go ahead.
And I should be Alice
There
again.
you are.
And you're the rabbit.
Okay, now we have to go to David's world.
Right. This little world
I'll
is
close
kind of
this guy.
show a very hefty kind of 3D environment.
There we go.
There's a little bit of a texture problem with this. I just got this machine and the drivers I don't think are quite ripe yet. But still, you see the environment's pretty rich. And what I'm going to do is go on top of the this aqueduct. I'm literally going to walk up there and walk up onto this. And Alan should be able to see me.
There you are. And one of the things that's cool here, just a little side comment, is my machine I'm using for this is an ultralight from Japan. So this is a 2-pound computer doing its stage of this stuff. And so we're basically at the point where 2-pound computers can do all of the computing that a child could ever hope for.
I'm to your right. If you just look, I'm at the
Oh, yeah,
very
there
end.
you are.
There.
So are you going to jump off?
Actually, what I'm going to do is, one of the things about 3D is distance doesn't mean anything in these virtual environments. So actually, I can jump to that window that you see way, way down at the bottom of my screen. I'm just going to just immediately go there, like so. I just did a quick, and then of course I can jump right back up.
Okay.
There I am. Ooh, what am I doing up there?
There you are.
Okay. Anyway, so I'm going to jump through the window again and out and back to where we started. And what's neat is I can seal Alan in before he gets out.
You got me.
He's stuck in the little world. Anyway.
Okay, so let's switch back. Okay, last couple of things here. Okay, so here, a couple of things about this system. So most of the 2D parts of the system were done by this group of about 5 people. And virtually all of the 3D system that you saw there, including the network stuff, was done by just 3 people. So the message here is, besides the fact that this is fun, at least we think it is, and that we think especially this kind of highly scalable stuff that doesn't require servers to do immersive stuff is a next interesting layer for the internet. If you think of it as a kind of an addition to TCP/IP as a way of handling n-squared problems. It also should be interesting to people who are interested in the future of software that this stuff was all done by a very small number of people. And that means that there's powerful leverage underneath in this way of building software, whatever way it is. One of the things we might talk about a bit is what way that is. My favorite statistic here, because this is a dynamic object system, I can use the dynamic objects as though they're a database. So here I have a retrieval, basically an expression that's asking all the compiled methods in the system to accumulate their size in bytes and add them up. So this will include the operating system, all the applications that you saw, the 3D stuff, development systems, and everything. So this is an interesting number. So it's 2.8 megabytes for everything. So that is a thing that's really worthwhile thinking about. The number of methods or things that are like subroutines there is about 50,000, which is too many. If I divide these guys into these guys, I get an interesting number, which is an average of 56 bytes per method in the system. About 230,000 lines of code, including the operating system. And we think it could be a factor of 10 smaller. And one last little Yeah. See, this is an interesting thing. Now, this is a beer game because I only mention this a little bit because one of the things that's fun about computing is you don't have to do a lot of bullshitting, because why not just write the code and do the demos? So the interesting thing is that this system is 2.8 megabytes and 230,000 lines of code. But in having Chinese lunches with the groups, one of the interesting things is to sit around and to think about kind of what is the actual entropy of the code. So for those of you who are, like an easy one that's very suggestive, for those of you who are familiar with 3D graphics and the math of 3D graphics can practically be written on a page because it's highly repetitive. It's basically has to do with being able to do a couple of different kinds of matrix transformations, and the most complicated part of it is the rendering stuff. But if you write down the actual math of it, it actually comes into this embarrassingly small part. And almost everything else that you wind up writing in order to do this stuff is optimizations of various kinds. So it's an interesting question of what does it actually take to prototype things if you could write the direct relationships and have those run fast enough to be interesting? What if you could separate out the optimizations in a way that they weren't commingled with the actual meaning of the code? So one of our projects that HP is going to fund next year is to try and take a whack at this actual question of how small could it actually be if you're able to actually go right at the thing and you had a nicer architecture than, say, Smalltalk's for doing this. I guess the last slide is, I believe software engineering right now is still an oxymoron. It just isn't here because there's nothing comparable to, for instance, the Empire State Building was put up by less than 3,000 people in around 11 months. That included demolishing the old Waldorf Astoria, which is on that site. So we couldn't organize 3,000 programmers to do some massive project in less than a year if we had to. So there is just nothing. If you use the word engineering as it's used today in civil engineering, there just isn't anything comparable in what, the kind of engineering we do is more like the Egyptian pharaohs did, of making large structures by piling up rock and then plastering it over with limestone. So, but I believe that the saving grace for doing this stuff, even more than the abstraction mechanisms, is the ability to do late binding. Because late binding has this property that when you're just at this part of most effort in the system, you get this horrible crash. You finally understand what you needed to know when you did the system, and if you're in a late binding system, you can actually go back and make those changes right now. And if you're in the way most people do software, you cannot go back. You say, well, we'll do that in the next system. And you know what? The next system never happens. Because that system that took so much time and effort that people decide to patch it for the next 35 years rather than doing this. So I believe in order to deal with a learning curve in a reasonable way, the number one thing, and it's a thing that I think the world first learned from Lisp. The greatest single idea in programming languages was Lisp, for sure, because of many, many things. But one of them is this notion of being able to late bind as many things as possible, including your meta system. And then the next thing I think that works for you is the abstractions. And maybe above all is to take heed from what the Engelbart programmers did, which is they just really wanted it to be that good, and they were willing to work their asses off to make it that good. So that's a very important part also. So time for questions? Any questions about this stuff?
what we'll do is we'll set up one microphone here, one microphone there. People
Okay.
can queue up.
Great.
Hold on.
Yes. The question that I had, I think that everything you're saying is right on the money. I do video games, and I believe that objects should have behaviors to be able to communicate. And I've been writing books about it for a while. How do you see, though, changing the entire paradigm of how everybody else thinks to try and teach them? And how long would that take?
See, I think one of the, again, I love these historical references. I'll just, at the risk of telling a one of the most brilliant things ever done on a personal computer was a thing done by Warren Robinette called Rocky's Boots. Anybody remember Rocky's? Oh, okay. Just one of the greatest things ever. Done on an Apple II. And what it was a little, it was basically kind of a maze of rooms. And you started off in a room and you had a couple of simple components. You had a little thruster and a little sensor, and you had a couple of and OR gates. And the objective was to wire up a little robot that would find its way out of this room. And so if you get the robot to do that, then you're in another room and it had more components and it was harder to get out of that room. And you just kept on doing this, and by the time you were at the end of this thing, you were pretty darn good at digital logic. It was just a fantastic, fun thing. And I have an Apple II solely to be able to run this old software. It's just great, although these days you can get good emulators. So a tremendous game that was derived from this, that turned out to be a failure, but just because of one slight flaw, was called Robot Odyssey. So the idea there, it's an adventure game. You're stranded in this city and you have 3 robots to help you and you can program them. And the adventure game is paced a little more like football. So it's not continuous action. You can use the robots to probe the next barrier you have to get through. The robots can communicate with each other. You can program the robots. So you can make a strategy. It's like a football play. Get the robots going and get to the next level. And children can learn a lot from doing those kinds of programming. So the stuff that we are primarily interested in is what we call hard fun. So we're not as interested in the game that's a ride as we are in the game that the child is a co-creator of what's going on. So like, for instance, a game that we would do in this system, this system is quite general. You can do EverQuest in it if you want to. But a game that we might do would be one where the child has to create things, to give them behaviors and stuff in order to get to the next step of the game and interact with other people in various ways. So I think if you look at that slide that I did about what happened with the printing press, it was unthinkable in the year 1400 when one person in 100 in Europe could read and write, and the Vatican Library, which is the largest library in Europe, had 372 books. And they knew there were 372 books in the Vatican Library because you can count 372 things accurately. But nobody knows how many books are in the Library of Congress. Right? So the change that happened was qualitative. Nobody expected that most people would actually learn how to read and write and think in a different way because of this stuff. So so my simple version of this stuff is that I think 2 things have to happen. We have to help the children not invent television when they start taking over this thing. Because the biggest problem with the inventive skills of children is they tend to be trivial. So like if you give them a piano, they'll invent chopsticks on it. But it took 200 years to develop real keyboard technique. So you have to help the children there, but you don't want to help them so much that they become mired in your ideas. So the idea is to help them enough so that they have a sense of taste and threshold, and then hope that the children will take it on to the next level. Because I don't think that we can actually quite imagine what the next level should be. Our theory when we were here at Park was, let's try and guess what the next literacy is going to be like and see if we can build something like it and see if the kids can take it the rest of the way. And in some sense, that's what I showed you today, is not what I think the next thing is going to be, but our guess at the best thing we could do for children so that they can take it the next level. It may not be a satisfying answer, but that's my answer. Other questions? Yes.
As we go back in the history of computing, I'm always astonished that it was the young kids that started it all. Seeing photographs of Bill Gates at 16 and so on.
Yeah,
and you're working with kids.
Yeah.
Is that environment possible today in 2003, that some kids in a garage will again create our next level?
I know. Well, there are two myths there. One is that Bill Gates had anything to do with computing. He had a lot to do with the economics of it, but I'm not aware of any advances that he ever made. And the other thing is there's a myth about the garage, which is the favorite American myth of all times. And the thing to realize is, and this is a hard thing that Americans hate, but like the two Steves in the garage, why were they able to do what they did in the garage? Because of all of the PhDs at Intel and Motorola who understood solid-state physics. It absolutely wasn't the way people love the garage thing. The stuff that has happened primarily because of PhDs. Park was full of PhDs. And we worked with children because it was a perfect balance between the two things, but it was not done by naive invention of tinkering things together at all, because it just doesn't work that way, right? So it was done by people who had as much knowledge as they could possibly put together and tried not to remember it most of the time. But the garage myth, I think, is, I think it was true for certain kinds of invention a long time ago, but it certainly hasn't been true since silicon became a critical factor and since higher level languages became a higher factor. So the interesting thing is what the children were able to do with real knowledge. So for instance, the Mac Finder, the Mac user interface, was actually done by Bruce Horn. And Bruce started with us at Xerox PARC when he was 12. And when he was 6 years later, when he was 18, he did the VM, virtual machine, for the Dorado for Smalltalk, which was a pretty hefty piece of work for an 18-year-old. But I still think Peter Deutsch's feat of understanding Lisp, and because most software people today don't understand Lisp of any age. So to have a 16-year-old boy be able to understand it and implement it is, to me, one of the most interesting things ever done by a teenager in computing. So, other questions? Yes.
Getting back to the kind of the technology behind all this stuff, I've noticed that the theme seems to be kind of higher and higher levels of abstraction and using simple things like scripts and sketches to leverage these huge algorithms underneath. And so I was wondering how you see, almost inevitably, artificial intelligence coming into this to kind of fill in the gaps even more so, things like neural nets for pattern recognition and fuzzy logic to make things more organic and all that, you know?
Well, I think there's two things. One is, one of the things I think we were all hoping for was at least one of the ways we thought computers could be different than a book, and I still think this is true, but it didn't happen, and it's not being funded now, is AI tutoring. Because a book should, a computer should be the book that helps you learn how to read it. Right? It can reach out to you in a way that a regular book can't, and turned out to be a hard problem. Some interesting special cases were done, but no general solution to it, because I think in certain cases it's worthwhile doing brute force versions of it, like for certain things about physics that you could spread out over billions of people. Why not spend, a couple of $1 million for each little thing? But it's been a real disappointment. On the other hand, I think that Seymour Papert's dictum was the question he asked was, should the computer program the kid or should the kid program the computer? So in our stuff, in spite of the fact that we abstract the optimizations away, we don't abstract any of the mystery. So basically everything is totally, in the sense that math is completely understandable, the stuff that we do is completely understandable. There's nothing like an AI ghost helping behind the scenes. So the children are very, very anchored in the cause-effect relationships that they're dealing with, and they are the ones that do the heuristics, like so when they will program the feedback routines, and they still know what it is that they're doing. So it's not like the invisible machine, or a much worse program like SimCity, where it does things and you don't know why it's doing things. You can't find out what it's doing, and you cannot change those things. So those things are very bad for children because they lead to superstition, like the real world. Other questions? Yes?
So going back to the example of the car, okay? So I'm wondering about I don't know how advanced the constraint solver or relationship maintenance system is, but how often, I'm curious how often children, it must have some limitations. I mean, there are fundamental limitations.
We don't use that at all. The programming of the car is done just like Logo. It doesn't use any constraints at all.
Right.
I mean, they're writing the relationships themselves.
Right.
You can think of them as one-way constraints if you want.
Okay, so that's, and do children ever try to find more advanced or establish more advanced relationships that bump into limits of the system?
Sure, because the essence of computing is nonlinearities, whether you want them or not.
Right.
And some of them are temporal. Some things are batched in such a way that you don't see some of the ones you might see in other systems. And sure. And but in the curriculum stuff that we do, we made up like 40 projects, of which 12 worked out to be kind of the projects that are the first 12 that children generally do, almost regardless of what their age is, from 10 on to even some 8th graders do about 12 projects. And these projects establish a couple of powerful ideas, having like the three powerful ideas that the children work with directly that are outside of the programming domain are this notion of increase by, and that goes in state. So that's a first-order differential equation, and if you do that into a variable and then use that variable and increase by into another one, then you get a second-order differential equation. And second-order differential equations model a lot of interesting phenomena. So those, and as I showed you, you can use them in data structures as well as out in the physical world. So you can do sampling. Like the first-order thing gives you sampling synthesis. And if you think about it, a second-order guy gives you FM synthesis. Right? You have to modulate that second guy because you have to speed up and slow down within the wavelength of the sample that you have. But that's basically what FM is. And if you look at it from the standpoint of phasors, which is the way I happen to like to look at things, then the entire synthesis mechanism is just piling phasors on phasors. And each one of them is basically one of these incremental guys. So the idea is basically that to take a few simple but powerful ideas and go deep on them within these projects. Second one is the feedback idea, which is a very nice one because it bridges the mechanical and the biological world. So there's a million feedback, besides the gradient following, finding lights. So feedback is kind of a general technique for making progress when you don't have complete information. Then the third one has to do with randomness and probability. Being when you don't want to know what else to do, you do something like, it's kind of like Monte Carlo. There's a whole set of heuristics built around that. If you think about that, those are three, if you had to pick three that encompass a lot of what's the way science thinks about the world, those three are it. And then, of course, there are powerful ideas from the programming itself, like the notion of a conditional, the notion of a loop, notion of a variable. Those are ideas that the students haven't really encountered before. It's usually quite late before we reveal to them that every little object in the system is a vector. So if you plop one of those guys into its own little thing, all of a sudden you can find that you can add these things to each other. So the thing that you thought, so you can add a car to a fire hydrant, and you get the vector sum of it. But that isn't introduced early. So think about it, and this is kind of a mathematical approach, because in math you don't want to, as Occam said, you don't want to multiply entities unnecessarily. So the idea is you try and stick to a few simple operative principles that have great range. That's why we call them powerful ideas. And but the people who very, very often run into barriers of many different kinds are adults. Because adults, when they're adult teachers, for instance, when they're learning, if they've had a little bit of HyperCard, they try and do what they learned in HyperCard. And it's very difficult for them to sit down and just learn a new system as a new system. They want to learn it as part of some other set of knowledge they have, regardless of whether that knowledge is powerful or not. So they are the ones whose questions we answer all. The kids are perfectly happy because from their standpoint, they're basically playing and creating their own toys, and they're happy to work within any system that is powerful for them. Yes?
One thing that I get a sense of you working with children, as adults, I guess when we get to be 20, 25, we get very serious in life. And I get a sense that by working with children, you brought play back into life at some level. and that's an important part of the whole creative process, plus enjoying life. One of the things that I was sensing when you showed all this, I could very easily see these mirrors. Each different mirror, let's say one of the mirrors was art, and you walk through the art mirror, and then you have all the different types of art, and then you could visually go to different impressionism, different types of art. Same thing with music. So I could see very easily this could be a whole kind of knowledge base that you could walk through, depending upon your level of interest, and start playing with these things in a way. And even because it's so visual, you can start connecting these things, maybe art to music to this, and there's a whole connectivity factor that could take place that in a way could make for an explosion in creativity, because we're all kind of focused in a particular paradigm, whichever we're in. I'd just like your comments on any of that.
Well, I think that's a good articulation of what the Augmentation of Human Intellect Center was doing at SRI. Right, if you look at what these guys were doing, and you can also ask Bill, since he was there and responsible for a lot of it. But basically, the idea was to try and make connections that when we did this system, one of the things that was kind of both amusing and exciting was at some point, I don't know whether it was you, I think it was David, because David had done a demo that was one of the greatest demos I'd ever seen, 10 years ago or something, that he had on these incredibly decrepit laptops that just barely worked. And it looked a little bit like what we showed there without the scope. But when we saw that, we basically said, wow, that's, we had this feeling like, this is like this and it's also embraceable. But we also realized that it's amusingly one-for-one with the structure of the web, but incredibly expanded, right? Because each kind of portal, there are things like bookmarks, that I guess we didn't show you, but you can take a snapshot wherever you are, and it goes into a little thing. You can just click on that and go there. So it's precisely like the hyperlinking that's done on the web. And each one of these vast 3D worlds is like a single page on the web, right? And you can have as many of them as you want. You can make as many of them as you want. You can link them in as many ways as you want. So you can just think of it as a more spacious way of thinking about using things. And of course, 2D is part of 3D. So the 2D. Yeah, switch the machines. Always have to be careful what you do.
That portal's open. You can go out, or you can just drop it right there.
So if I take this guy and toss him out here.
Can you switch the machines again? Is anybody up there? There
No.
it is. Oh, we still have that bug.
Yeah.
Is that an artifacted hardware difference?
Which?
The display we saw?
No.
Yeah, there's a driver problem. This is a very new machine, and the driver is not managing OpenGL textures quite right. This is actually using an older NVIDIA chip, and so that's actually a lot more robust. In fact, this is a lot better than I updated the drivers recently, and it's dramatically improved over what it was. So give me a couple of months, and they'll fix it, and it'll be even better.
So
sorry about that.
One interesting thing here is, though, that I can reach in here and do the 2D stuff. All the 2D stuff is mapped into the 3D world, right? Because it's just graphics. So, but I think one of the things we didn't say is you shouldn't take this user interface too seriously. We just did this for the demo, to have something neat to demo, and it was a nice way of paying tribute to David's ideas of 10 years ago. But in fact, the system, as we showed you, is late bound, so anybody can make their own worlds and user interfaces. There's nothing actually nailed down. Yes?
You're preaching to the choir here. This is all great stuff, really cool stuff. How do you recommend getting this out to a larger audience?
Teach more people to sing? I like that metaphor. Well, I think that's what it's about. This is poetry rather than prose. Yes?
When I was a kid in school, I used to get bad grades because I'd sit there and be bored, and then I'd come home, and instead of doing homework, I'd invent acoustic delay lines and stuff like that. And now I'm working in
You're
aerospace.
lucky they didn't lock you up.
Well, maybe you're right. I'm dangerous, but now I'm working in aerospace, and I'm senior enough that I'm advising people and so forth. And it's the same syndrome. I sit there and I'd be bored, and I go home, and I'm working with better equipment on more sophisticated projects in my garage. Does your work with children hold any promise to break that paradigm?
Well, it's hard to say because there was a point in the around 78 or so when I guess Adele got sort of discouraged about the thing. I did too, but at some point I couldn't think of anything I wanted to do more. So it was kind of like I learned how to play pipe organ at age 40. I had been a professional musician a long time beforehand, but it was just a lot harder than I thought. And I finally succeeded in doing it just by slogging a few hours each day, regardless of how I felt. And the children's stuff turned out to be infinitely harder. I figured it was a 10-year problem when we went to Park. That we had the advantage of stuff that Seymour Papert and other people had done. We had the advantage of Piaget and Montessori and Jerry Brunner. So there was enough stuff there that seemed like 3 or 4 turns of doing user interface and real experimentation was going to get it. But it didn't get it. And part of the problem took us a while to realize that we didn't even know when we were getting good results or not. And sometime in the early 80s, we started realizing that we got some tremendous funding from Apple. So we're in a school for a long period of time. And we noticed that the third year on some of the things that we've done, we were getting much better fix on how a curriculum. The first one of these was a curriculum that didn't involve computers. It was a design curriculum that involved city building stuff. And this curriculum had been tested on older kids, and it was beautiful curriculum. And it took 3 years before it started happening at the above threshold level. So it wasn't just, dicking around with milk boxes, but it actually became serious systemic design of complex things like cities by third graders. And that was a huge revelation to us, and also gave us a sinking feeling. Because, my God, if you have to do 3 years in a classroom before you can know that you're wrong, because you have to normalize everything else. The teacher has to get comfortable with the curriculum. Still might be a bad curriculum, but they still got to get comfortable. Technology is never right, so you have to grind it. It has to be better than mil spec because you've got 64 kids hanging on it. So it has to be better than most things people sell in stores, and yet you have to be able to change it weekly as you're going along. And then what we generally got was, oh, this isn't good enough. But, a little bit, so the progress on the thing was kind of interesting. One of the turning points that led to this current system was just because we were in this school and with a lot of funding, we had a full-time videographer. And the kids had gotten used to her, and after a couple of years, she was invisible. And one day, for the hell of it, we said, well, let's do a whole thing on what kids do when there's no adult supervision. So she spent 6 or 7 weeks shooting stuff out on the playground when the kids were out in recess, and put it together into this incredible 30-minute compilation. And, it was Lord of the Flies and then some. But it got us, it was just one of these things which everybody knew, but we didn't know, that kids are anthropological creatures. That is, it gave us a perspective on what was actually going on. And one of the most important things is that a truism that everybody knows, but we rarely do a great job designing for, is that different kids have different motivations. And so once we realized we had the curriculum stuff down, we just didn't know how to, what the environment should be. We started looking at the motivational stuff. And a lot of the elements in this system were put in there so that the child who's intrinsically interested in ideas, which is like 5% of them, can see that this is for them. The child that's the hero of their own fantasy. And all you have to do is watch children play, and you can see the child in which every play thing they do is to support this hero's quest that they're on. And we wanted the child to see this system as something that was for them. And the children do very, very, once they do like the drive a car thing, what they do when they do their next project, which they make up on their own, is very, very different, but it falls into patterns. And so the success of this system was that virtually all, for instance, some children are social. They mainly want to do things because other people are doing them. It's not just girls. It's a motivational type. So there's a lot of this, the ability to talk to kids all over the world through this system, to get mentoring from other kids throughout the world. It's important for all kids, but especially for those kids. So the key on this thing, and the key to actually answering a little bit of your question, is we can't wait for the adults to reform. Because remember, they are part of an organization that took 100 years to set up. And so in a typical school district like San Jose, no one on the school board knows anything about real math and real science. No elementary school teacher knows anything. No principal knows anything about it. Most parents don't. The state legislature doesn't. If you look at the science standards for the state of California, some of them are dead wrong, and they don't care. So it's a cargo cult full of a dozen different factions all going through rituals. And there's enough of them so it seems like it's a reasonable set of behaviors. So it's a hermetically sealed, endless cycle of futility, because real subject matter never gets contacted in any way. So the way to short-circuit that stuff, to some extent, is one of the things that we did that I didn't show explicitly here, but you can get the idea that if a child gets stuck on doing a project, then they can open up a flap that looks like this, their friend's flap,
You want to switch machines?
Oh. Yeah, switch machines.
Can you switch the machines again?
Yeah.
There. Magic.
So here's their friends flap. And these are people who have done this project last year and have signed up to be mentors. Tommy here might be in Germany, and Sam might be in South Carolina, and so forth. And if they're online at the time, their badge is lit. So they can just go to one of these things, and they can do screen sharing and stuff as we've shown you. And we have internet telephony built in, so they can just talk to each other and say, hey, I've got this problem, and the other kid can come over and say, yeah, well, why don't you do this? And once they fix that thing, then they can start doing some joint project, which usually involves in some kind of game. So the just-in-time stuff can be readily handled by mentoring. The problem is depth. Is if you think about the mentoring of child to child, it's hard to get depth there. You know, it's adults' responsibility to provide depth and threshold. And this is the hardest thing to do in a way when 95% of the population of the U.S. doesn't have it. They just don't have depth. And an enormous number of adults believe that if you are an adult, you know enough to teach a 6-year-old child. And that is absolutely, totally wrong. It may have been right 20,000 years ago. Probably not even right then, but it's absolutely not right now. The people who know the most should be the ones teaching the 6-year-olds, who have the most understanding of where this stuff is going to go, because you're building foundations. As Montessori pointed out, the whole purpose of being young and learning through play is to build up your heuristic stance towards the cause and effect relationships in the world. And the heuristic stance of the 20th and 21st century is not the same as the 11th century. That's our problem. Because we can teach direct knowledge as much as we want, but if the students retreat, if a child retreats back to the same old common sense when they don't have a case-based answer to the thing, we haven't taught them a damn thing. And science is primarily a different epistemology and a different, an uncommon sense. And if you're not teaching the uncommon sense, you lose, no matter what else you think you're doing. So this is the dilemma. This is why helping the helpers is the #1 problem in making this stuff work. Trying to do it through the official school system could take forever, though. So is this a good place to quit?
I think we do have to quit. We're supposed to be out of here at 9:30, but this gentleman here has been sort of patiently waiting for one last question, so we'd like to give him the opportunity to do that.
I'll try and make my reply uncharacteristically brief.
And first of all, I would like to thank both you and Dave for just a wonderfully engrossing and challenging evening.
Okay.
And again, I want to ask all of you again, we really would appreciate your feedback on this series and what we might do in the 2003-2004 year. My email address again is rockowitz@minsoft, that's MINSOFT.com. So I hope to hear from you. And now Rajiv.
All right, thank you. Alan, when you spoke, I think here in the late 80s, you talked about the problem with...
Always give the same talk.
The problem with the evolution of software was this problem of carpenters versus architects and the value of aesthetics.
Well, I'm glad I didn't use that one tonight.
But
it's true.
The value of aesthetics in creating artifacts. So are you at a point with this system where once kids become facile, you begin to notice or see some emergence of those things, or are they taught?
So, I mean, the simplest, like if you take the 2 girls who did the car going down the middle of the road. So I was actually, because the original design of this system, which was called eToys, was actually for a kind of an internet experience. It wasn't really designed for a big educational experience for kids. It was designed for kind of an internet experience. And it was one of the teachers we'd worked with for many years. And our incredible executive director, Kim Rose, decided they wanted to try it in the classroom. And I felt that the system had some real limitations because I designed it mainly for fun. And I left out a few things I thought were important. And about 6 weeks into the thing, they showed me that car going down the thing. I looked at that and I said, holy shit. That is a really nicely thought out program, because it's just as clean as can be. They realized it was two separate cases, that the overlaps in the cases didn't matter. And there it was. And I looked at the other solutions, and the 20 children in that first test came up with 5 different solutions. One was even more elegant, which was one pair of kids realized you could do it with 3 parallel scripts. That basically you could and this is kind of my friend with the constraints. Right. So this is an interesting way of thinking about it. So these 2 kids went even further. They realized, it didn't actually matter. The synchrony didn't really matter that much. So why not just write 3 parallel scripts? It was easier for them to think about. So they had a conditional in each one, and essentially the same conditional, but it was 3 guys running at the same time, and that was really biological in character. And it's now we're not so surprised by those. But when I first saw that, I thought, gee, that is beautiful. That is a really nice solution, because they weren't trying to jam the conditionals into each other like we might. But I think the best example, there are a couple of examples I didn't show you, but remember Tyrone with his, now you can hear the tone of his voice talking lovingly about the solution that he did. And he actually had to go to quite a bit of extra work to drop those cookies down there. But he just absolutely wanted to show, this was his way of doing a proof that he had nailed, had completely analyzed what was going on there and had built a model that just exactly did the thing within the limits of measurement. And if that isn't aesthetics, I don't know what it was. And I happened to be luckily present at a couple of moments for Tyrone when he was doing that. In 2 different parts of this thing spread out over a couple of weeks. There were some really beautiful things where I just accidentally watched him change his frame of mind. When he just, all of a sudden he was in this thing where his mind had gotten big enough to encompass the whole thing, and he was just grooving on it. And anybody who's ever done this stuff, anybody who's ever loved math or programming and loved a beautiful program or a beautiful thing of math, they know what this feels like. And you can recognize it instantly in a kid when they're doing it, because they just love it. They just absolutely love it to death, and they talk about it with that particular tone of voice that is so compelling. So Tyrone has a lot of zen. I mean, he really, he was not atypical in that a little more than 70%. This is the first time we'd ever, this test, by the way, is not in this 3 years of testing, is not a real test, because we're doing the 2nd year right now. Real test will be next year, but even in this first shot, 70% of the kids in the class got above the fluency threshold on this thing, which just astounded me, because I had predicted like 30% at the most, because I designed that thing for high schoolers. And once again, I was wrong. So it's just never ceases to amaze me that if you do the right pacing with kids and you have an appropriate representation system for them, their ability to think is, as good as our best thinking. What they don't have is a full set of representations to think with, and they don't also have little experts in their head that are dealing out possible heuristics, so they tend to get stuck more often. And people who have done this, particularly the kindergarten schools in Italy, the Reggio Emilia schools, have discovered that even preschoolers can do amazing things if you just give them more time. So you can teach preschoolers to do unbelievable feats of counting and arithmetic if you spread it out over maybe a factor of 5 more time than you'd take with a first grader or so. And so that was a really interesting thing. And we've only been just appreciating that in the last few years as to how important pacing is for the kids. So that's just something to take away, perhaps. I have a feeling that this stuff applies to adults as well. If you look at college if you don't really know what's going on in college, you're in trouble in the deep subject courses because the pacing is looking for coverage rather than depth. And so if you don't have enough time to get depth, then you're lost, right? So I think this is something that works in more areas than the children. So it's 9:30. Thank you very much. It was a pleasure.